All right, we take up a new topic, chemical kinetics, today. We've been talking about thermodynamics, where our focus is always on the eventual outcome. We just say things are mixed and they come to equilibrium, right? That says we give them as much time as it takes for that to happen. In kinetics, we're going to look at just how long does this going to take? How long do processes take to happen? What is the rate or the speed at which they take place? That you could imagine would be an important consideration if we were, say, in the chemical business and we wanted to be making a product to sell it. Knowing how long it takes to make it would be an important part of our business plan. Right? So there's clearly a need to know some of these things. So the main question in chemical kinetics is how fast is a reaction going to happen? What is the rate of reaction? The speed at which it takes place. Okay. If I say my equation says I can convert this many moles of reactants into that many moles of products, how long will that take? There's a second category of questions we'll talk about a little bit, which involve just how does a reaction take place? What is the so-called mechanism for the reaction? That looks at just how exactly do the reactant molecules get converted into the products? What has to happen? What's the first step where maybe a bond gets broken and then some other bonds start being made? And we'll look a little bit at how we can get some information about that. That's a fairly complicated subject, but for relatively simple reactions, there's a decent amount known about how those reactions take place, and we'll at least touch on that a bit. To think about these questions, we're going to have to consider the path taken by the reactants to the products, right? So we're now no longer going to be able to just make up a random path, like taking everything apart, breaking all the bonds and just having atoms and then rearranging them. We're going to have to rely more on just experimentally studying reactions and measuring how fast they go and figuring things out from there. So let's start by defining the rate of a reaction, right? The odd-looking chemical equation up there is meant to be a generic reaction. I wrote it with two reactants and two products, but that's a sort of arbitrary choice. The ordinary letters A, B, C, and D represent the chemical substances. So think those are chemical formulas there. The Greek letters alpha, beta, gamma, and delta represent the coefficients that would balance the equation, numbers of moles, okay? In the equation below, which defines the rate, okay, all of those different expressions would be equal to the rate of reaction. You see that they've all got a delta, and then they've got a substance in square brackets. Those square brackets on the top of each one of those fractions, those always represent the concentration. So whenever you see a formula in the square brackets, think molarity, okay, because that's what that's going to be. So they've all got the change in concentration over the change in time. The small lowercase t is time there. So in units, that's going to be moles per liter or molarity on top, right? And on the bottom, I'm going to have something like time or seconds. Okay, so those are going to be the units that concentration will generally come in is molarity over time. Notice that on the A and B terms here, we've got minus signs. Okay, the reason for that is the concentrations of A and B would be going down as this reaction proceeded, right? Because they're the reactants, they're getting used up. If I measure the amount of A in the beginning and then measure it after a while, I should have less A. So the change in the concentration of A is going to be negative. Putting that minus sign there assures that the rate is defined as a positive quantity. Lastly, notice that each one is divided by its coefficient. That's because the rates of change of the different substances will depend on the numbers of moles that are in the equation. Right? Suppose that in my equation that 1 mole of A reacts with 2 moles of B. Right? In that case, the concentration of B would be going down twice as fast as the concentration of A, because every time I use up 1 mole of A, I use up 2 moles of B. Right? And so dividing by those coefficients would assure that I got things that were equal. This says I can define the rate in terms of any of the substances, but once I define it, this gets me the same value no matter what one I've picked. Okay. In reality, if we were studying a reaction to choose which one we were going to measure the concentration of, we would probably just pick which one is the easiest to measure, right? If there's something that if it's in solution, is one of the things colored, and could I measure the intensity of the color, just how deeply colored the solution is, by putting it in some sort of spectrophotometer. You've hopefully seen those in lab, and then we could measure concentration that way, for example. But that would just be a what's easy to measure kind of question. So the rate is influenced by a lot of different things. The first point on there is a maybe trivial one, which is that different reactions will go at different rates. Okay, even if they look kind of similar, hydrogen plus iodine, hydrogen plus bromine, those reactions could have very different rates. Okay, so every reaction goes at its own rate. There's not just one universal speed of chemical reactions or anything like that. The physical form of things will matter, right? Are things dissolved in solution? Are they solids? Are they in the gas phase? If there's a solid involved, is the solid one big block of stuff, or is it ground up into a fine powder? That actually could change the rate of reaction by a lot, because things in a solid that's reacting, probably only the parts that are on the surface will get to react. So grinding it up should make it go a lot faster. The concentrations are generally very important, right? We saw that the rate is defined by the change in concentration. Reaction rates usually depend on the concentration of reactants. Sometimes they depend on the concentration of products, and once in a while they can depend on the concentration of some other species or substance. It doesn't seem like it has anything to do with it. That's kind of an unusual turn of events, but it does happen sometimes. Temperature changes the rate of a reaction, and it changes it by a lot. Okay, there's a rule of thumb among chemists that says for a lot of reactions taking place near room temperature, if you raise the temperature by 10 degrees C, you can double the rate of reaction. Okay, that's a big change for a fairly small temperature change. Okay, the fact that reaction rates change significantly with temperature is one reason why if you have a bit of a fever, your body starts to feel really rotten, right? It's because the rates of different reactions in your body are getting out of whack with one another, and that causes problems. That's one of the main reasons why a high body temperature makes you feel rotten. So we'll talk about temperature dependence in another couple of days. We'll talk a little bit about catalysts. A catalyst is a substance that can change the rate of reaction. Generally, we think of wanting to speed it up. A lot of industrial chemistry relies on catalysts to get reactions that might otherwise be very slow to take place faster. And we'll talk a little bit about how that can happen, how that works. So for the rest of this video, what we're going to talk about is rate laws and one reasonably simple way to find a rate law. Okay, so if my reaction is just A plus B makes products, whatever the products are, it is generally true, it's most often true, that the rate will be equal to some constant K times the concentration of A raised to a power times the concentration of B raised to a power. Okay, that's essentially an empirical observation. People have studied the rates of lots of reactions and they tend to go that way. N and M in there are known as the order of reaction. So in this case, N would be the order of reaction with respect to A. M would be the order of reaction with respect to B. N plus M as the overall order of reaction. Now, a nice thing about N and M, these orders of reaction, is that these orders of reaction are usually small whole numbers. Right? And that makes it especially easy to find them, it turns out. In particular, the vast majority of them are either 0 or 1 or 2. It turns out there are some cases where we get small rational fractions, like a 1/2 or something like that can sneak in there. But for a vast majority of reactions, they're going to be one of those numbers. Okay, people sometimes talk about the sum of the exponents there as the overall order of reaction. Okay, so if N was 1 and M was 2, I could say that overall the reaction was third order, right? K, the constant in there, is not a constant like Planck's constant or Avogadro's number or anything like that. K is what's called a rate constant. It's a constant only for a particular reaction at a particular temperature. Okay, so it's not something you can just look up in a list of numbers in the front cover of a textbook or anything like that. It's a very specific thing for a reaction at a temperature. Right. If we change the temperature, that would change the value of that rate constant, generally substantially. So we have to be careful that we're only comparing data that are for the same reaction at the same temperature when we work with these rate laws. So a warning about those orders of reaction. You can't tell what the order of reaction is by just looking at an equation for a reaction. Okay, it's tempting. You can imagine that'll happen sometimes because the coefficients in the balanced equation are very often small whole numbers. The orders of reaction are small whole numbers, and so sometimes they're going to match. But that's not a rule. They don't have to be the same. So I wrote down here a couple of reactions that in both cases, they have 2 moles or molecules of one substance as the reactant, right? At the top, I have 2 N2O5s. On the bottom, I have 2 NO2s. It turns out experimentally that that top reaction is a first order reaction and the bottom reaction is a second order reaction. There is no way that you can look at those equations and know that. There's no way I can look at those equations and know that unless I just happen to remember what I know about those reactions. Okay, so you can't find the orders of reaction by looking at the equation. You can only find them by doing experiments. Right, that's really important. Keep that in mind. Unfortunately, a little later on, we'll talk about something that will make it harder to keep this idea straight. But do try to get that cemented in your understanding right at the beginning, that we have to find those things experimentally. So we're going to talk about 2 different ways to find rate laws, one in this video and one in the next. The first one is something known as the method of initial rates. It's the most intuitive way, kind of. And then we'll talk about integrated rate laws, which are a bit more mathematical. We'll talk about those in a separate video. Okay. In the experimental approach for this method of initial rates, what I do is I say that the time when I know the concentrations the best is right at the start of the reaction, right? Because in that case, I know how much of each reactant I've got. If I'm going to pour 2 beakers of solution together, I know what the concentrations are, and I can know them very accurately at that beginning moment. I know I have no products before I do the mixing, right? Then I let my reaction go for a short interval. How long is a short interval? It depends on how fast the reaction is, right? It might be as short as microseconds or something like that, or it might be a few seconds. Just depends on the speed of the reaction under the conditions we're doing it. Okay. Then I measure the change in one of the concentrations. Maybe I can measure how much product has formed in the first couple seconds or something like that. Then I would know that the change in that concentration was that amount that had formed divided by the time it had taken, right? If I repeat the experiment using different initial concentrations, I can see what happens to the rate, and from those we can find the experimental rate law, okay? The easiest way to get wrapped around this is to look at an example. So here goes with an example. This, I confess, is it's a made-up example, right? A and B are just randomly made-up substances here, right? I don't like to do that, but for some reason I have that here just because it's easier to make a nicely behaving set of numbers that way, okay? So in each row here, let's label these. I should have put some more tags on here. So let's call this experiment 1, experiment 2, and experiment 3. Right? So each row represents a separate trial of my experiment. My rate law, I want to be saying that the rate is equal to K, a rate constant, times the concentration of A to a power, let's call that X, and the concentration of B to another power, let's call that Y. All right, that's what my rate law should look like. And my goal here is to find the values of X, Y, and K. I'm trying to find 3 things, and that's basically that's the reason why I need to have at least 3 experiments in my data table here, because I've got 3 different values that I'm trying to find. And so in some sense, I need 3 separate independent equations in order to do that. The good news about these is that if you're at all comfortable comparing numbers, you can usually reason your way through these without having to do significant math. So let's talk about that. In the data, let's see, the experimental data here are not maybe the most friendly in terms of how they were collected, but they're not the worst. So let's look at experiment 1 and 2 here. If I look at those 2, what has happened? The concentration of A has not changed, right? So anything that happens to the rate there would have to be due to the concentration of B. The concentration of B has doubled going from experiment 1 to 2, but the rate has not changed, right? So that says doubling B does not change the rate, okay? And that tells me that my order of reaction for B, this is a slightly weird example to start with, but my order of reaction for B must end up being 0, right? Think about it this way. If I doubled B, if Y, the exponent on B, was 1, then doubling the concentration of B would double the rate, right? Given that my concentration of A is fixed because it's the same for those 2 experiments, right? If Y was 2, if it was second order in B, then doubling the concentration of B, I would then square that, and doubling squared would mean the rate would be multiplied by 4. But it's neither of those two things, right? So I'll write up an equation-y version of this in a minute, but for now I'll say it's relatively easy, and I think most of you are understand exponents and stuff well enough to say that from the fact that that doesn't change, I can say that b has to equal 0. Right? Because if b is non-zero, not b, if y, sorry, the exponent on b, y is equal to 0, right? Because if y is anything but 0, then changing the value of that concentration of b would change the rate, and it didn't. Now I know that b doesn't matter, right? Because b to the y power where y is 0 is just 1. So this is now just k times the concentration of a to the x power. Now I don't have to worry about the B concentration anymore, right? As long as there is some B, there has to be some of it there, otherwise the reaction can't work. So now I can take, let's say, experiments 2 and 3 down here. If I look at those two, I'm not paying attention to B anymore because it's getting raised to the 0 power, which makes it kind of disappear from my equation. I double the A concentration, right, from 0.1 to 0.2, and what happens to the rate? It goes, if I just ignore the decimal places, it changes from 32 to 128, right? So the concentration was multiplied by 2. The rate over here was multiplied by 4. So that says I need to have 2 to some power, give me 4. And that should tell me that x, my exponent on the A concentration, is equal to 2. All right. If I do that, that would give me that my rate law now is equal to k times the concentration of A squared. All right, suppose you are not seeing how that works. Let me do a little bit of an equation-based explanation, and then I'll come back and get the numbers and figure out the value of the rate constant after we do this, okay? So let's try explaining this. Let's say I'm going to write the rate for experiment 1, which I'll just call rate 1, that's equal to k, the rate constant, times the concentration of A, which was 0.1, and that gets raised to the x power, times the concentration of B, which was also 0.1, raised to the y power, okay? Then I'm going to write the same expression for the second experiment. K is still the same because all my experiments had to be done at the same temperature. This piece is still the same. This one is now 0.2 to the y, and this is equal to 0.0032, and so is this one. Okay, so now I have those two equations there. There's a general rule for doing algebra that says I can divide equal things by equal things, and I still get equal things, right? So that says if I divide these two expressions here and divide those two, that now I still have an equation which says that k, actually let me just cancel some stuff, right? It says the k's are going to cancel. The 0.1s to the x power are going to cancel, right? Because that's why that was constant. So I've got 0.1 to the y over 0.2 to the y. That's equal to 1/2 to the y power. And that has to be equal to 1. And that should make me understand or make me realize that y has to be 0. Right? If it still doesn't click for me, then I could take the logarithm of that, I guess, and I would get y ln 1/2 equals ln of 1, right? And that would again give me that y has to be equal 0. Okay. If I did the same thing using the rates for 2 and 3 and already knowing that y is equal to 0, then I could eliminate that and get the power that I got for the x exponent on there as well. Okay, so hopefully one way or the other, those will make sense. With a little practice, I think as long as the numbers are friendly, it's a little bit tricky if the concentration, instead of doubling, just changes by some random amount. But if you were doing the experiment, you would often just say, well, I'm going to make it easy on myself. I'm not going to multiply the concentration by 1.742 or something. I'm going to multiply it by 2. So I can just tell, looking at the numbers, what's going to happen. All right, the last thing it asked us to do was to actually find the rate constant, okay? So let me use the first row here, okay? So in the first row of that table, experiment number 1, as I called it before, I had concentration of A equals 0.1. I had concentration of B also equals 0.1, although I don't really care about that one anymore. And I had the rate equals the number up there, 0.0032. And that had units of molarity. Remember, capital M is molarity for us, and then it had minutes for a time unit down there, okay? Now I know that my rate law says rate come on. The rate is equal to K, the rate constant, times the concentration of A, and A is squared, right? Because my exponent X turned out to be 2 when we solved for that part. So if I put the numbers in here, that gives me 0.0032 molarity over minutes. And that's equal to K times 0.1 molar squared. Really, that was a 2. So if I try to solve that now, I'm going to solve for K, right? And I'm going to get K is equal to 0.0032. That still has units of molarity per minute. And then I'm dividing that by 0.1 molar, and that's squared. And when that's squared, the molarity unit gets squared along with the 0.1, okay? And if you divide that out, I have notes next to me that tell me that I get, and I really probably shouldn't need them for this, I guess, 0.32. Now this has units of 1 over molarity times minutes. Okay, so the units are a bit strange looking. I'll have a comment on units for rate constants momentarily. Okay, so once I know what the rate law is, then I could pick any one of the rows of that table, right? I happen to have picked the top row, but if I had picked another one, I should get the same result, right? As long as I have the right rate law. So we could do that as a check to make sure that we had it right. All right, I promised a closing word about the rate constants and their units. Rate laws have a form that says the rate is equal to rate constant times a concentration raised to a power, okay? The rate itself always has units of concentration over time because it is the change in concentration divided by the change in time. So that says because the molarity on the right-hand side is going to be raised to the x power. So the rate constant will have different units depending on the order of reaction. Okay. In practical terms, that means you can't do a problem where you're solving for a rate constant and do what some of you do on some other problems, like get to the end and say, oh, it's a rate constant and the units for that are always this. Right? I know that many people, if you're doing like a problem finding delta H, you get to the end and you say, oh, that's always in kilojoules, right? You can't do that for rate constants. You have to actually make sure you pull the units through the equation to make sure you're getting them right, okay? So watch out for that. In our next video, we'll look at a second route to finding rate constants from experimental data when we talk about integrated rate laws.